Imagine a big toy box that holds many different toys. Each toy can do something special. A car can roll, a doll can talk, a puzzle can be solved. A Python module is like one of those toys. It is a file that holds code that can do a specific job. Why use modules? Reuse, you can play with the same toy again and again without rebuilding it. In code, you write a function once and use it anywhere. Organization. Just as you keep cars in one shelf and dolls in another, modules keep related code together, making it easier to find. Collaboration. If you and a friend each bring your own toy box, you can share toys and build bigger games. In Python, different people can share modules, so large projects become possible. Maintenance. If a car's wheel breaks, you only fix that one toy, not the whole box. Updating a module fixes many programs that use it. Overall, modules make programming cleaner, faster, and more fun, just like a well-sorted toy room. Explanation: creating a module is as simple as writing a Python file, for example my_math.py. Inside, you can put functions. Hash my_math.py. Define add open parenthesis, a comma b close parenthesis, colon return a plus b. Define multiply open parenthesis, a comma b close parenthesis, colon return a times b. Importing works like opening a toy box to take a toy out. In another file you write. Import my_math hash brings whole box. Print.my_math.add open parenthesis 2, 3 close parenthesis hash uses the add toy. Or you can pick only the toys you need. From my_math import multiply. Print multiply open parenthesis 4, 5 close parenthesis. Structuring many modules together is like arranging shelves. You can create a folder // with an init.py file. It can be empty. Put several modules inside. /init.py geometry.py stats.py. Now you can import with a dotted paths. From mitools.geometry import area_circle. This keeps code tidy, just like labeling each shelf with its toy type. Best tip for kids: think of each .py file as a small notebook where you write recipes functions. When you need a recipe, you open the right notebook with import. When Python looks for a module, it follows a treasure map called sys.path. The map is a list of folders like : import sys print sys.path. Typical entries are : the folder of the script you are running, your current room. The site packages folder where pip puts extra toys. Any extra folders you added later. Namespace is a fancy word for name tag. When you import a module, its functions get a tag that says which box they came from, so two toys with the same name do not fight. Example: import math, import random, print math.py, print random.py. If you only import the name : from math import py, print py. But be careful: if another box also has a py, the later import will overwrite the earlier one, like two kids wearing the same name badge. You can change the search path by adding a folder to pythonpath, environment variable, or by manipulating sys.path at runtime : import sys and os. Append to sys.path the absolute path of my extra modules. This tells Python to also look in my extra modules for toys. Managing the path wisely prevents module not found errors and keeps the playground organized. Pip is the shopkeeper that gives you new toys packages from the Python market. Installing a package: pip install numpy. The shopkeeper goes to the internet, finds the numpy box, and puts it into your site packages shelf. Upgrading to a newer version, like getting a newer edition of a board game: pip install -- upgrade pandas. Removing a package you no longer want, maybe the toy is broken: pip uninstall matplotlib. How pip works: it reads a list called requirements.txt. Each line is a package name and optional version, for example, numpy == 1.26.0, pandas greater than or equal to 2.0.0, less than 3.0.0. Running pip install -r requirements.txt tells pip to fetch exactly those versions, so everyone playing the game uses the same toys. Tip for kids: think of pip like a vending machine. You type the snack name install numpy and it drops the snack the code into your pocket, your computer. When you build a Lego castle, you might need many different brick sets, and each set may rely on other small pieces. In Python, a dependency is a package that another package needs to work. Pip tries to solve the puzzle for you, but sometimes two packages need different versions of the same brick. That is a conflict. Virtual environments are like separate playrooms. Each room has its own shelves of toys, so the red bricks in one room don't mix with the blue bricks in another. You create one with Python-mvenv myenv, source myenv/bin/activate, on Windows myenv \scripts \activate. Now every pip install goes only into myenv. When you leave the room, deactivate, you return to the main house. Reproducibility means anyone can build the exact same castle later. By saving the list of installed toys, pip freeze greater than requirements.txt, you capture a snapshot. Later you can recreate the same room with pip install-r requirements.txt. This is crucial for scientists because their results must be repeatable, just like a recipe that gives the same cake every time. Analogy: imagine you and a friend each have a toolbox. If you both use the same screwdriver, same version, you can share work easily. If one tool is older, it might not fit the new screws. Virtual environments keep each toolbox tidy and avoid mismatched tools. If you have built a cool toy, a Python package, and want to share it with the world, you can put it on PyPy, the Python Playground store. The steps to publish you. Prepare a folder with your code and a setup.py or newer piproject.toml. Example setup.py contains, from setup tools import setup find packages. Then call setup with name equals awesome_math, version equals 0.1.0, packages find packages, description equals simple math helpers for kids, author equals your name, Python requires greater than or equal to 3.8. Build distribution files, a source zip and a wheel, with python-mbuild. This creates dist/awesome_math-0.1.0-py3-none-any.whl. Upload to PyPy using Twine. First install Twine with pip install Twine, then upload with Twine upload dist/*. You will need a PyPy account, like creating a username for the store. After upload, anyone can run pip install awesome_math to get your package. Why the store? It gives you a safe place where people can verify the package's origin, read its description, and see its version history, just like a library catalog for toys. Scientific libraries are like superhero toolkits for numbers. NumPy gives you fast arrays. Think of a row of Lego bricks that you can add, multiply, or reshape instantly. Example: compute the sum of squares of the first 5 natural numbers. Import numpy as np. Nums equals np.arrange16. Squares equals nums squared. Result equals squares.sum. Print result. Mathematically, sigma sub k equals 1 to 5 of k squared equals 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared equals 55. SciPy builds on NumPy and adds higher-level tools like solving equations. Suppose we want to solve the quadratic equation at x squared plus bx plus c equals 0 with a equals 1, b equals -3, c equals 2, using SciPy. From SciPy import optimize. Define function f of x. Return x squared minus 3 times x plus 2. Roots equals optimize.fsolve function f03. Print roots. The math says the roots are x equals 1 and x equals 2. Practical workflow. Create a virtual environment, python-mvenv sci-env. Install the libraries pip install numpy scipy. Write a script, analysis.py, that imports them, does the calculations, and prints results. Share the script and the requirements.txt, pip freeze greater than requirements.txt, so others can repeat the experiment. These libraries let you do heavy math in a few lines, just like a calculator that can also draw graphs and solve complex problems. Writing good modules is like making a sturdy Lego set that other kids can safely play with. Versioning, use semantic versioning, numbers like major.minor.patch, for example 2.1.3. Increment major when you break old code, like changing a brick shape. Increment minor when you add new backward-compatible features, adding extra wheels. Increment patch for tiny bug fixes, fixing a loose screw. Documentation, think of a manual that tells how to build the set. Use docstrings inside functions and a readme.md with examples. Example docstring. DefGreet takes a named string and returns a string. The docstring says return a friendly greeting. Parameters name a string the person to greet. Returns a string a message like hello Alice. The function returns hello name. Tools like Sphinx can turn these into nice web pages. Security, treat your code like a door lock. Validate inputs, never trust that a user will give a safe number. Avoid using eval on unknown strings. It is like letting a stranger open the safe. Keep dependencies up to date, pip list outdated. Use a security scanner such as Bandit to find common mistakes. Putting it all together, when you release a new version, bump the version number, update the changelog.md with what changed, run tests, build the package, and upload to PyPy. Others can then safely install your package equals 2.0.0 knowing it works and is documented. This habit keeps the Python world tidy and trustworthy, just like a well-organized playground where every toy has a label, a guide, and a safe lock.